We're going to start by reviewing some oxidation states that you learned in Chem 151. So this is our diagram of a periodic table, and for ionic compounds, you can do the charges by looking at the periodic table. This does not necessarily work with covalent compounds, but in ionic compounds, group 1 has a +1 charge in a compound. Group 1 metals. Group 2 metals are +2. And then going across the periodic table, +3. This column doesn't really form ionic compounds, but sometimes I call it plus or minus 4. And then you go back down, -3, -2, -1. And this is the noble gases. They don't really form a lot of compounds, so we don't worry about their charges. All right, so for example, with sodium chloride, sodium is a group 1 metal, so we would expect it in an ionic compound to have a +1 charge. Chlorine is in the halogen column, so we expect it to have a 1- charge. And that's why it is 1 sodium and 1 chlorine, because they cancel each other out to form a neutral charge, a neutral compound. Another example would be magnesium oxide. Magnesium's in group 2, and it is a +2. And oxygen is in this column, and it is a -2, and that is why there's only 1 magnesium and 1 oxygen. So in 151, you remember predicting the charge of magnesium to be +2 and oxygen a -2. And when you crisscrossed, you might have thought it was Mg2O2, but it had to be the lowest ratio for an ionic compound, and that is where you got the MgO for magnesium oxide. Now, those are very simple relationships. For the transition metals, a lot of those have variable charges. So you had to determine what their charges were in the specific circumstance. For example, let's do this compound right here. All right, this has 3 elements in it, and it's based on a polyatomic ion. So we look at the ones that we do absolutely know the charges of. Potassium should be a +1 because it's in group 1. Oxygen is a -2. Now, all the charges have to balance out because this is a neutral compound. So I have 4 oxygens at -2 each, gives me a total contribution of a -8 charge. Potassium, there's 1 of those, so that's a total contribution of 1. And I'm trying to figure out what the manganese is. And I see that this is a neutral compound, so it has to add up to be 0. So just kind of looking at this simple algebra, X is equal to +7. So the manganese is a +7. All right, let me do one more example that's with a charge. So what if we have the bicarbonate ion? HCO3 1-. So this is charged. This is not neutral. This has a total charge. All the charge must add up to be this total charge. All right, so hydrogen should be a +1. Carbon, we may or may not know, and sometimes it's questionable, so let's leave that one to check what it is. And then each oxygen is a -2, but I have 3 of them, which means I have a total of -6 from that oxygen. And this has to add up to be a -1. So if you actually wanted to do the algebra, 1 - 6 is going to give us a -5 equal to -1. So +5 +5 So 5 minus 1. So X is equal to positive 4 for that carbon. All right, so that's a couple of different ways to do this. There were some transition metals that have very specific charges all the time, like silver is always a +1. Zinc is always a +2. Gold is always +1. And cadmium is always +2. Oop. All right, the rest of them you usually have to use the formula to determine the charges. Now, why is this important? We are getting ready to balance redox reactions and study electrochemistry, and it's all about the exchange of electrons. And we have to know the charges in order to know how many electrons are being exchanged, which will lead us to oxidation and reduction. All right. So I'll erase that in a moment. We're going to start with our redox reaction. So here is the example I'm going to use. It's iron 2+ with dichromate going to iron 3+ plus chromium 3+. And just based on what's given, you can tell this is not balanced. There's oxygens missing. Some of the atoms are balanced, but not all of them. But we have to also balance the charge and the electrons. All right, so the steps are listed for you in your lab manual, and I'm going to go through those. So the first step is to separate it into the half reactions. The easiest way to do that is to group the like elements. So I'm going to take the iron and group that together. And I'm going to take the chromium stuff and group that together. Those are my half reactions. Now, I can look here and determine what's being oxidized and what's being reduced by evaluating all the oxidation states and how the charges are changing. But it is not necessary in order to balance the equations. Today we're focusing on balancing the equations. Later you will have to do other things to make sure you know which one is being oxidized and reduced. Okay? All right, so we're going to go through each of these half reactions and apply these steps. So the next step is balance the atoms other than oxygen and hydrogen. Oxygen and hydrogen are special, so don't tackle those first. Go to the elements. Here, other than oxygen and hydrogen, we have iron and chromium. So I have one iron here, one iron here. So the iron's balanced. The charge isn't, but the atom is. In the second half reaction, I have 2 chromiums and 1 chromium. So this matters. I need a 2 here. All right? So now those atoms are balanced, and I've completed step 2. Step 3 is where we balance the oxygens, but we don't just throw in oxygen. Oxygen gas is not involved in every single reaction, but most of our reactions happen in solution. So there's plenty of water around. So we're going to use water to balance the oxygens. Now in the first reaction, there are no oxygens, so there's nothing to balance. In the second one, we have 7 oxygens here, but no oxygens over here. And water has 1 oxygen. So, in order to get these 7 oxygens balanced, I need 7 waters. So now I have 7 oxygens. And again, I didn't have any oxygens in the first reaction, so there was no need to add any water. And then the next step is to use H+ to balance any hydrogens that are in these reactions. Again, the first reaction, it's very simple. There's only iron in that one, so I do not need to add any hydrogen. In the second reaction, I didn't have hydrogen before, but now I do. I have some water there, so I have to make sure those hydrogens are balanced. So I have 14 hydrogens. The way I balance those hydrogens is to add 14 over here. I do caution you to be careful. Oxygen might be in multiple places. Hydrogen could be in multiple places, so you have to take the total into account. All right. So now all of my atoms are balanced. I'm going to step 5 where I add electrons to balance the charge. And this may seem tricky, or it's not really tricky, but your brain can play tricks on you. All right. What's the total charge here? +2. What's the total charge here? +3. I need to add electrons to one side in order to make both sides equal in charge. What charge does an electron have? All right, so electrons, one electron, we represent it like that, has a -1 charge. So every time you add electrons, you're going to bring the charge down. So you're always going to add electrons to the most positive side. So add electrons to most positive side. All right, so that's going to be +3. In order to bring +3 down to +2, I need 1 electron. So +3 and a -1 equals +2. All right, now I'm missing the rest of my charge here. It's a 2 negative. Determining total charge is not always as simple as looking at just the charge on the ion. You also have to look at the stoichiometric coefficients. So I have 14 plus, I have a 2 minus, which gives me 12, plus 12. On this side, water is neutral, so I have 2 plus 3's, which is a +6. The most positive side is the +12. How many electrons? 6 electrons. So I'm going to add 6 electrons over here. The whole point in balancing a redox reaction is the charges have to be equal. A substance is being oxidized, which is losing electrons. The electrons that are lost are the same electrons that are gained when the other substance is reduced. So right now, my 1 electron does not equal my 6. I have to make them equal. right? So, in order to make them equal, I am going to multiply this by 6. And I'm going to start rewriting this reaction now. It's getting a little messy. I do not recommend writing every step out. I would write it on the same reaction. Like, don't rewrite the reaction for every step. Just do it all, follow the steps, but do it on the same reaction. So, but I want to leave this up here, so I'm going to rewrite it for you. So when you distribute the 6, you will get 6 Fe 2 plus goes to 6 Fe 3 plus 6 electrons. And then our other reaction, I'm going to keep the arrows aligned because that's very helpful. I have 6 electrons plus 14 H plus Cr2O7 2 minus goes to 2 Cr plus 3 plus 7 waters. So now that my electrons are equal, they're not going to end up in my balanced chemical equation because they will cancel out. If you remember doing mechanisms, remember we looked at intermediates and catalysts canceling out to give you an overall reaction. This is sort of the same thing in looking for what cancels. In this instance, the electrons are the only thing that cancels. Sometimes you might have waters that cancel, partially cancel, and hydrogens that partially cancel. So what I'm going to do is add these together. So 6 Fe 2 plus 14 H plus Cr2O7 2 minus goes to 6 Fe 3 plus 2 Cr plus 3 plus 7 waters. And then if you wanted to make sure this was balanced, you could go back to like you did in 151 and just count all the atoms on each side, making sure you have the same number of irons and hydrogens and chromiums and oxygens. But when you get done, the charge is also the same on both sides. So let's just confirm the charge. All right, so we have 12 plus 14 is 26. Minus 2 is 24. And then 18 plus 6 is 24. So the charge is the same on the both sides, and you can confirm the atoms. Now, this is for acidic solution. pH less than 7. So pH equals 1, this is how you would balance it. pH equals 2, this is how you would balance it. If you're given a specific pH, there is nothing specific to do except whether it's acidic or basic. If it's in the acidic range, you add your waters and your H pluses. So the next step is making it basic. How do we do that? Basic is the same thing. So we've already made it acidic. The next step is to take it to basic. So if I give you a question where you have to determine it in a basic solution, you still have to start with acidic and get to this point. Now we're going to make it basic. And I try to relate it to a titration, even though I know that's not your favorite topic right now. I am just going to convert the acid to base. All right? So watch this very closely. I have, after you get done canceling out, because both reactions may have H plus in it, but your final equation should only have H plus on one side. I'm going to take this H plus. I have 14 of them. If I were titrating 14 moles of H+, how many moles of hydroxide would it take? If I have 14 moles of H+, and I add OH minus, how many OH minuses is it going to take to get rid of the H+? H plus is 1 plus, and OH minus is 1 minus. So it's going to take the same number, 14. So plus 14 OH minus, but I just spent all that time getting all these things balanced. So I can't just put it on one side because then it's not balanced anymore. I have to put it on both sides. Now, an acid plus a base, and we don't have the counter ions here, the spectators. We just have the net here. What is H plus and OH minus going to make? It's going to make water. How many waters? It's all a 1 to 1 to 1. It's going to make 14 waters. But now I have 14 waters and I have 7 waters over here. So I have to reduce that and make sure it cancels. But not all of them will cancel. So in this particular case, all 7 of these will cancel and leave me with how many waters over here? 7 waters. All right, so this looks kind of ugly. So let me rewrite it. My final answer in basic solution would be 6Fe2 plus 7H2O plus Cr2O7 2 minus goes to 6Fe3 plus 2Cr plus 3 plus 14 hydroxide. So now it's in a basic solution. The reaction is MnO4 minus plus H2C2O4 goes to manganese 2 plus CO2, and it wants to balance it in a pH equals 14, which just means basic. So we'll go through the steps to make it acidic and then take it to basic. So the first step is to separate it into the half reactions. So I have this thing with manganese and this thing with manganese. So I'm going to do MnO4 minus goes to Mn plus 2. And my other one is H2C2O4 and CO2. So the next step is balance the atoms other than hydrogen and oxygen. We correct those with water and H+. All right, 1 manganese, 1 manganese. H, carbon, 2 carbons. So I need 2 carbons over here, and then that takes care of all of my atoms other than oxygen and hydrogen. And the next step is to balance the oxygen using water. So in the first half reaction, I have 4 oxygens and no oxygens over here. So I am going to add 4 waters to get 4 oxygens. In the next step, I have 4 oxygens here and 4 oxygens here. So be very careful. If you don't look at this coefficient, you'll think there's only 2 and incorrectly add 2 waters. All right, so I have 4 oxygens, and then this is also 4 oxygens. So no waters there. Now I go back and balance hydrogen using H+. So I have 8 hydrogens here, so I'm going to put 8 H pluses on that side. Down here I have 2 hydrogens, no hydrogen, so I'm going to put 2 H pluses over here. So now all of my atoms are balanced. I have to work on charge. Total charge here, I have 8 plus and a minus, so I have a plus 7. Here I have plus 2. Add electrons to the most positive side. Add enough to bring it down equal to the other side. So positive 7 is the most positive, and it will take 5 electrons to get it down to plus 2. Down here, I have 0, and over here I have 2 plus. The most positive side is the 2 plus, and it will take 2 electrons to make it equal to 0. Because there's no charge written with it. The reaction was given. This top line was given and there's no charge there, so that's how I know that there's no charge here. All right, now we have to make the electrons equal. The electrons lost have to be the same as the electrons gained. This is 5 and this is 2. So the lowest number of electrons we can transfer here is going to be 10. So I'm going to multiply this whole thing by 2. And this whole thing, 5. And this whole thing, the first one, by 2. So I have 10 electrons plus 16 H plus 2 MnO4 minus plus 5 H2C2O4 gives me 2 Mn plus 2, 8 waters. You have to be very careful to distribute this to each one. Sometimes after the arrow, we tend to leave it off. All right. 10 CO2s and 10 H pluses. But I need to cancel, and 10 electrons to be complete. So the whole point is to make sure the electrons cancel on each side. So my electrons cancel. What else cancels? That's right, H plus cancels. I have 16 here. And I have 10 here. So my higher number, I'm going to have some left over. All 10 of these will cancel and leave me with 6H plus over here. The other thing you would look to cancel is water. In this case, I only have water on one side, so it's not going to cancel. So in acidic solution, it'd be 6H plus 2MnO4 minus plus 5H2C2O4 gives me 2Mn plus 2 plus 8H2O plus 10CO2. But I need to make it basic. To make it basic, I focus on my H pluses. I have 6 H pluses here. So I'm going to add 6 OH minus to both sides because I want to keep all my atoms balanced. I can't throw something in on one side without throwing it in on the other after I have everything balanced. The 6H plus and OH minus are going to make 6 waters. And after you make water, you have to double check your water. Because you could be combining some waters on one side or canceling out waters. So I have 8 H2Os here and 6 H2Os here. All 6 will cancel and leave me with 2 H2O. So my final balanced equation in basic solution will be 2MnO4 minus plus 5H2C2O4 goes to 2Mn plus 2 plus 2H2O plus 10CO2 plus 6OH minus.